On July 19, 1969, the Apollo 11 Command Service Module and the LEM Lunar Excursion Module entered lunar orbit. The time required to travel once in orbit is called the orbit period. This was approximately 2 hours and at an altitude of 113.46 kilometers above the moon's surface. You will use this information to determine the mass of the moon. First thing I'm going to do is just highlight the important values that we're going to use for our calculations. So 2 hours, 113.46 kilometers, and what we're trying to find is the mass of the moon. So to the right is our diagram, and you can see the 113.46 kilometers is actually just the surface above the moon. And when we're doing calculations involving r, so you'll notice r shows up here, it's actually the distance between the two objects that are interacting. So the module is orbiting around the moon, and we are looking at the distance between their centers of gravity. So technically, we would also need to know Part 1. Assume that Apollo 11 went into a circular orbit and that the gravitational force and centripetal force are exactly equal. Solve Fc equals Fg for the mass of the moon m in terms of v, r, and g. Set the equations equal to each other, simplify, and rearrange to get m alone on one side of the equation. So we are going to set Fg equal to Fc. And we're going to substitute Fg for everything that it's equal to. And we're going to substitute Fc for everything that it is equal to. So what we're doing here is we're just setting that equal to that. And we're going to rearrange so that we can isolate m. So it's all by itself, and it's like we're solving for m. And we're going to keep everything in variable form. We're not going to substitute any numbers in there just yet. All right, so we know that Fg is equal to Fc. We also know that Fg, the force of gravity, is equal to big G times big M times little m all over r squared. And Fc is equal to little m times v squared all over r. The first thing we can do is cancel out some of the terms. So little m is on both sides of the equation. We can cancel it out. We can also cancel out an r on the right side and one of the r's on the left side. Now I'm going to rewrite the equation to clean it up. So I have g times m over r is equal to v squared. We're not quite done because our goal here is to solve for m. So we want to isolate it. We have to get everything on the other side that is not m. So the first thing I'm going to do is multiply r on both sides of my equation. Cancels out on the left side. And just to be extra clear, I'm going to rewrite my equation to clean it up. So I have g times m is equal to v squared times r. My final step is to divide by g on both sides. Leaving us with our answer, which would be m is equal to v squared times r over g. Part 2. By using the fact that for circular motion, v equals 2 pi r divided by t, re-express your answer to problem number 1 in terms of r, t, and m. So this will be another substitution, but we're going to substitute 2 pi r over t into velocity in our answer to the previous problem. So that looks like m is equal to v squared. So now I'm going to substitute this right here. So 2 pi r over t, and that whole thing is going to be squared. And then we multiply that by r. And now the whole thing is over g. So we just substituted what v is equal to into the equation that we just solved for previously. All right, so now we need to simplify this. And it says to re-express your answer in terms of r, t, and m. So to simplify this, it's a little weird when you're squaring a fraction, but the square is going to go to every single thing that's in the fraction. And once you know that, it makes it a lot more straightforward. So the next line of algebra would be m is equal to 2 squared is 4. Pi squared is, I'm just going to leave it as pi squared. And then r squared, well, just r squared, all over t squared. And I'm just going to leave this in parentheses to try to keep it neat. I'm going to multiply that by r. And then this whole thing is over g still. All right, we can simplify this a little bit further. I can see that there is r here and there's r squared there, so I'm going to combine those two things. So that's going to become, and so this just becomes r cubed. And I'll get rid of the parentheses now. This looks pretty confusing the way it's written. And so whenever I have problems like this, when I have like a fraction in the numerator and have to divide by something, it really helps me to rewrite this like this, divided by g. And when you're doing division and that involves fractions, remember to get rid of the division symbol, you can multiply by the reciprocal. So we're going to multiply by the reciprocal of g, which ultimately just becomes 1 over g. I'll just do a new line of algebra here. So m equals 4 pi squared r cubed over t squared times 1 over g. And we get 4 pi squared r cubed all over t squared g. And that's our answer. So I'll rewrite it one more time neatly. M is equal to 4 pi squared r cubed all over t squared g. And that's our answer for part 2. Part 3. Measure the total distance that the orbiter was from the lunar center, so the altitude plus moon radius, and convert from kilometers to meters. This is R. Convert the orbital period 2 hours to seconds. This is T. G is the gravitational constant, which is 6.67 times 10 to the negative 11. Write out each quantity with its associated variable. All right, so R, the distance from the lunar center to the distance at which the orbiter is away from the moon. So we're going to add 1,737.13 kilometers. Plus the distance of altitude, so 113.46. I just added those two numbers together using Desmos, and I got 1,850.59 kilometers, and then to convert that to meters, you have to multiply by 1,000, and so here is my final answer. Now for the period. The period is equal to 2 hours, but that needs to be converted to the SI unit, which would be seconds. And to do that, I'll do some dimensional analysis, and I know 1 hour is equal to 60 minutes. And I know that for every 1 minute, there are 60 seconds. And to convert, first I'm going to cancel out all of my units that are diagonal, just to prove that I'll end up with the unit of seconds. And the final calculation I need to do is just multiply everything in the numerator together and divide by everything in the denominator. So that would be 2 times 60 times 60, all divided by 1 times 1, which I'm not going to bother writing because it's just going to be whatever I get. Everything multiplied together. So I'll put that in Desmos. 2 times 60 times 60, and I get 7,200. All right, lastly, we have G, which is and all those little letters, those are just the units, so it's meters cubed per kilograms times seconds squared. But the actual number that we're using in the equation is just 6.67 times 10 to the negative 11. So it's a very small number. All right, so now that we have each of those numbers, we are ready to calculate M. you will plug in what you know about r. So I'm just going to leave this part blank. And that whole thing is going to be cubed. And we'll divide that by t squared. And so that's something else that we need to substitute in. And there you go. So finish up this problem, and when you're all done, you're going to take a picture of all your work. I'd like you to separate it by each section. I just put boxes around the different sections, and you could do something similar, and that would be great.